All right, so welcome everyone, and this is my second class on atomic structure, or rather the atomic theory. And in today's class, I'm going to focus mainly on four major things. And the first one, or let me write them down, even if I don't follow the order, it's fine. I still want to discuss all of these things in this class. So I'm going to talk about atomic orbitals. I also want to talk about the concept of quantum numbers. I also want to talk about electronic configurations. Electronic configurations and hybridization. So these are all very, very important concepts of atomic theory. And I'll make sure to say by the end of today's class, at least we know all the necessary things that we want to talk about on these particular principles. So to just get back on speed, remember last time we met, we already discussed what an atom is, and we described an atom as the basic or the fundamental unit of matter. And we continue to say atoms are usually made up of subatomic particles. In specific, we mentioned three subatomic particles. We mentioned three subatomic particles, of which we described these as we have protons, we have neutrons, and we have what we call electrons. Like this. So we said protons are found in the nucleus, or these two protons and neutrons like this, these are found in the nucleus. Then we say the protons are positively charged, whilst the neutrons are not charged. They are neutral. And we say we have electrons that are found in what we call shells or energy levels. And they have a net charge of negative. Like this. So these are the important subatomic particles that we talked about, and we say these guys are found in the atoms, which we described as the fundamental or basic unity of matter. And we continue to say protons are the ones that describe or that act as the number plate of an atom, because the number of protons directly relates to the atomic number of that atom. Also say the number of protons and neutrons. So the atomic number, let me write it down here. The atomic number is related to protons, and it is known as Z. The atomic number is known as or represented by the letter Z to represent atomic number, which is just giving us the measure of the protons or the number of protons that we are having in the nucleus of an atom. And we say the combination of protons and neutrons that are in the nucleus are going to give us what we call the atomic mass or the mass number of that particular atom. So say the combination of these two is going to give us what we call mass number. And the mass number of an atom is given or represented by the letter L. I mean A rather. So we say the mass of these subatomic particles, they of course have different masses. For example, the proton, we say it has a mass of one atomic uh, mass unit or one AMU, one atomic mass unit for the proton. Say the neutron also has a mass of one atomic mass unit, of which this can also be referred to as the Dalton, in honor of the scientist who discovered these things. So even the neutron has mass of one Dalton, which exactly translates to one atomic mass unit. And say the mass of an electron is negligible. These guys that are found in the energy levels, their masses are negligible, which means we can just neglect the mass of electrons when we are considering the mass of an atom, just like that. So since the overall charge of the subatomic particles that are found in the nucleus is positive, because of the proton being positive, whilst the neutron is neutrally charged, we say the net charge of the nucleus is positive. So nucleus, say Z positive, whilst the shells or the energy levels, they are only containing the electrons that are negatively charged. Hence, the overall charge of the energy levels are or is negative. And also, we mentioned to say since the electrons are the ones that are found in the energy levels, these are the guys that are responsible for taking part in chemical bonding or chemical reactions like that. So those are very, very, very important concepts that you'd love to know in this topic of atomic theory. Now, to continue on what I've just mentioned on uh, on the electrons, I also mentioned to say using the Heisenberg uncertainty principle, it is difficult. It is difficult to actually predict the the exact position and the momentum or velocity. Why does this keep on rubbing? Momentum or velocity of a certain electron at a certain or given time, because these guys are continuously spinning around the nucleus in what we call shells. So since we can't predict the position and velocity of an electron at a given time, that's why we just view, or when you view an electron under an electron microscope, what are you going to notice? We're going to notice that these shells just appear as the electron clouds. Electron clouds, because you can't really tell the position of an electron and its speed, so it's continually spinning, and the only thing you can see when you look at it is uh an electron cloud. So these guys can, or by appearing as electron clouds, there are also some more specific spaces, or some more specific spaces in these electron clouds that we are usually having a higher probability of you finding an electron at a certain time. And we call these subshells, of which these subshells are going to contain what we call orbitals, like this. So this is just to add some brief information on what we already discussed last time, or in the first class when I introduced this topic. Okay, so this is or this is just a brief introduction, and I would now want to continue to where I wanted to discuss today, or continuing from where I've just stopped here to say we have or shells are the ones that are, or the spaces where we find the electron in an atom, although they are appearing as electron clouds, and these guys are actually designated by what we call principal quantum numbers. Principal quantum numbers to represent the shell, and these numbers, or the principal quantum number, can actually vary. These are positive integers starting from 1, can be 2, can be 3, just to show the number of shells that a particular atom has. So or has. So we are going to understand that bigger atoms are going to have large numbers when it comes to the principal quantum number, because the quantum number is just showing us uh, uh, how big an atom is, which means it has more electrons, hence having a higher quantum number. And the higher you go in terms of a quantum number, it means you are also increasing the amount of energy. What does that mean? That means, for example, this is a nucleus. We're going to have principal quantum number 1 closest to the nucleus, principal quantum number 2 second closest to the nucleus, principal quantum number 3, and so forth and so on. So you're going to notice that as you move away from the center of the nucleus, the energy levels keep on increasing. So that means as we are increasing the principal quantum number, even the energy of the electrons is increasing. The lowest being the first one, followed by the second one, followed by the third one. So which means the third principal quantum number, the electrons that are occupying the shell with the third principal quantum number, or principal quantum number 3, have higher energy as compared to electrons that are occupying the shell that has a principal quantum number 1, because we are increasing in quantum number. So this one is less than that, and that one is also less than this. We can actually consider them like that. And sometimes you're going to notice that electrons are actually going to change their principal quantum number. Electrons can change their principal quantum number. What do I mean? I mean electrons can move from either the electron of lower energy or the shell of lower energy to a shell of higher energy. You can say maybe an electron has transitioned from the first shell to the second shell, or from the second shell to the third shell, or vice versa. What do I mean? An electron or transitioning from the third shell to the second shell, or from the second shell to the first shell. And what does this depict? That means if an electron is moving from the third shell to the second shell, that electron is losing energy. Energy has been lost by that electron, and it has transitioned to an energy level of lower energy than the previous one. The opposite is the case when you're transitioning from 1 to 2, because here there is gain of energy. An electron is gaining energy. And how does these electrons actually gain energy? It is in different ways, of which the most notable one that I can talk about is mostly by absorbing of light, of which this light in chemistry or in biology or under this topic of atomic structure, we call it a photon. Like this. So when an atom or when an electron or absorbs a photon, it is going to do what? It is going to increase its energy level since it's absorbing some type of energy like this. Whilst if it loses a photon, that means that electron is going to go into an energy level of lower energy, because there is energy that has been lost. So that can explain the principle of photons and transitioning between electron shells or energy levels or electron clouds, whatever you can call them. So these electron shells that we've talked about are actually also subdivided. The electron shells are subdivided, and they are divided into what we call subshells. So inside a shell, you're going to find what we call subshells, and these subshells are labeled using 4 letters, and we call these the S subshell. We have the P subshell. We have the T subshell. Whilst we also have the last one that we call the F subshell. And these subshells that I've talked about here are going to correspond to distinct shapes and also having a specific capacity of electrons that it can actually contain. For example, if we talk about let me go to another page there. If we talk about the S subshell, the S subshell, the S subshell contains one orbit. The S subshell contains one orbital and can accommodate a maximum of 2 electrons. So the electrons I'm putting here are maximum number of electrons. Then we have the P subshell. And this one contains 3 orbitals. Like that. And this can actually have a maximum number of 6 electrons. We have the D subshell. The D subshell contains 5 orbitals and can carry a maximum of 10 electrons. Whilst the last one is the F subshell. The F subshell. And this one has 7 orbitals. And they can carry a maximum of 14 electrons. So remember, we already discussed what an orbital is. To some, this maybe might sound like a new word, but I already discussed what an orbital is. I said we are having electron clouds, and we can't predict the exact position or momentum of an electron. That's what the Heisenberg uncertainty principle states. Hence, we have some specific areas, or the areas that have a higher probability of being found, or of us finding an electron in that space at a given time. And those specific positions or those specific areas are what we call orbitals. These guys are found inside the subshells that are found inside the shells. Okay, so that is that on the shells, the subshells, and also the orbitals, describing to us the number of orbitals that each subshell actually has, and the maximum number of electrons that uh, uh, each orbital can actually accommodate. Okay, so from here now, I can move on to what we call quantum numbers. So what are these things that we call quantum numbers? So in short, if I want to describe them in the simplest manner that I can say, I'll just tell you to say these are a set of numbers that are going to be responsible to give us the actual address of an electron in the shell. So these guys are giving us the electron's address. In a specific shell. How are they going to give us the specific address of an electron in a shell? It's because they actually are just a set of unique values that are going to describe precisely the properties and behavior of an electron within an atom, just like that. So those are what we call uh, quantum numbers. They're going to be responsible to give us the exact position of an electron in an atom. And they actually do so by defining or for giving us the specific information for each electron that we can find in an atom, such as the the or defining the energy of that electron, its special distribution, its distribution in space, special distribution, but also the spin the spin of each and every particular electron. So primarily we have four quantum numbers, and these are what we're going to discuss about. So we have four quantum numbers in total that are going to help us describe the actual position of an electron in an atom by giving us or helping us to identify these three things that I've talked about. Okay, so what are the four quantum numbers that I'm talking about? The first one is what we call the principal quantum number. The principal quantum number. The principal quantum number, which is represented by the letter N. So what is this guy known as the principal quantum number? This is I've already talked about this actually to say it is going to define the electron's primary energy level and the overall size of the orbit that this electron is occupying. So we say it's represented by the letter N, and it actually takes positive integers. N can be equal to positive integers such as 1, for example, 2, 3, 4, and so forth, and so on, and so forth. So these are just telling us the actual shell, the actual energy level, and the overall size of the orbital that a particular electron is actually occupying. So I've already discussed with you to say when you have higher numbers of n there, what is happening? It is actually corresponding to larger orbitals and the larger energy electrons, which means an electron is having higher energy, hence being in a higher energy level, and also having a higher average distance from the nucleus of an atom, because the further you are from the nucleus of an atom, the higher the energy you have. So this is just actually directly relating to the electron shells. Okay, so that is the first one that we call the principal quantum number. The second one is what we call the angular momentum. Angular momentum, also known as the azimuth, the azimuth quantum number. So what does the angular momentum quantum number do? So this guy is represented by the letter L, who I forget, or small l, a small letter L, lowercase l, whatever I can describe it as. Okay, so the angular momentum or azimuthal quantum number represented by the letter L, and what does this do? This guy is responsible for telling us the specific shape of the orbital, and is going to also define the subshell in a given energy level. So we've moved on from the energy level. We're now talking about what? The specific shape of the orbit and the definition of the subshell within a given energy level. So this guy, or this quantum number, this particular quantum number, is also represented by numbers. And these numbers can range from zero to n minus 1, like this. The principal quantum numbers can range from 0 to n minus 1. And where is the n coming from? The n is coming from the principal quantum number. So you can see, to say slowly by slowly, we are getting to the actual address of the electron using these quantum numbers, because I say the angular momentum, this one is going to tell us the shape of the orbit, and its subshell, and the specific subshell, and not to say orbitals, are found in subshells. So the numbers that define the angular momentum quantum number are ranging from 0 to n minus 1. And we're going to also understand that each value of L that we get is going to indicate a distinct shape of an orbital. Distinct shape of an orbital. For example, if we have L is equal to 0, since we said 0 is the lowest, L is equal to 0, that means this is corresponding to an S orbital, which is having a spherical shape. If L is equal to 1, we're going to have a correspondence to the p orbital. And the p orbital, the shape of the p orbital is a dumbbell shape. So you can see that as we move on from the higher values of the angular momentum quantum number, the shapes of the orbitals also keep on getting more complicated, because as you move on, some orbitals have to accommodate a large number of electrons. We talked about the s orbital only accommodating 2, the p orbital accommodating 6, the d orbital accommodating 10, and the f orbital accommodating 14. So you can see the shapes getting in more complex and complex due to the number of subshells that are there, indicating a large number of orbitals. So when L is equal to 2, this is corresponding to what? To a d orbital. And the shape of a d orbital is having very, very complex shape, just like I'm from explaining. But one of them that we can give is a cloverleaf. This is the signature that they will ask you about. If they ask you about the shape of d orbitals, you can just give this one. You can just give that one. The fourth one, L is equal to 3. And this corresponds to what? Corresponds to an f orbital. And this one is also very complex, but you can just say it's a multi-lobed. Multi-lobed in terms of shape, and that caters for all the angular momentum or azimuthal quantum numbers that you can actually talk about. The third one is the magnetic quantum number, ML. magnetic quantum number is represented by the letters ML. And what does this do? This is going to indicate for you the actual orientation of that particular orbital in three-dimensional space. Remember, I said quantum numbers help us in also identifying the spatial orientation of your electron. So this quantum number, this particular quantum number, the magnetic quantum number, is responsible for telling us the orientation, how a particular orbital is oriented. Orientation of orbitals in 3D space, in three-dimensional space. Space like that. So it has ranges of -1 to +1. What does that mean? That means it can either be -1 or 0 or +1. And what do these numbers actually mean? So the number of possible magnetic quantum numbers that you have, values for a given angular momentum quantum number, the L that we talked about in the previous page. So the number of these possible magnetic quantum numbers, they are also going to depend for each given angular momentum quantum number, and it is going to determine the number of individual orbitals within a subshell. For example, if you have L is equal to 0, remember we said when L is equal to 0, that is what? That is an S subshell. Subshell like this. If L is equal to 1, that is a P subshell. And so on and so forth. So this magnetic quantum number now can be -1, or it can be -1, 0, or +1, indicating that there are 3p orbitals, which means in the 3p subshell, this one, there are what? There are 3p what? 3p orbitals. In the 3p subshell, there are 3p orbitals. That's what all these three numbers are actually representing. And that's how this magnetic quantum number can also help us in predicting the actual position of an electron in an atom. Even for the s orbital, ML for the s orbitals is we said it can only accommodate 2 electrons, is 0. ML is equal to 0. And what is this indicating? It is indicating that there is only one orbital in the S subshell, whilst in the P subshell we have ML, which can be equal to -1, which can be equal to 0, which can be equal to +1, indicating that we have 3 orbitals in the P subshell. And these 3 orbitals can actually be written as Px, Py, and Pz. The 3 p orbitals that are described by the ML, which is equal to -1, 0, or +1. Okay, so that is about the magnetic quantum number. Now let's move on to the last one, which is the spin quantum number. The spin quantum number. The spin quantum number. So the spin quantum number is represented by NS, or MS rather, and this is just going to show us the angular momentum of an electron, which is also known as the spin of an electron. So this one is going to show us the angular momentum or spin of an electron. Like that. So why are we having this type of a quantum number, which is giving us the spin of an electron? It's because electrons mostly they behave as if they are spinning, and by so doing, they are going to be creating small amounts of magnetic field. So because of that, we have allowed values for spin quantum numbers that can be positive half or negative half, like this, describing the two states of spins, or I can say the two possible spin states of an electron within a specific orbit. And this is very important for understanding how electrons are going to pair up within an orbital. And we're going to explain this more using what we call the Pauli's exclusion principle. So that is all when we talk about the quantum numbers. This was the fourth quantum number, and we've actually seen how important these guys actually are. To summarize everything, so we have the principle, which gives us the energy level and orbital size. We have the angular momentum, which are going to give us the shape of the orbital. We have the magnetic that are going to give us the orientation in 3D space or orbital orientation space. Whilst we also have the spin quantum number, which is giving us the electron spin direction that can be plus 1/2 or negative 1/2 to help define the electron spin state within an orbital. So those are the four quantum numbers that I wanted us to look at. And from here now, we can move on to another important thing, which is the orbitals themselves. We've been talking about orbitals, S orbital, D orbital, P orbital, the F orbitals, but how or what's the science between these spaces that we're calling orbitals? So let's get into them. Orbitals. And what am I going to focus on? I'm going to focus on the shape mostly and the spaces. Okay, so I've been describing orbitals. I've been defining orbitals, whatever manners or different languages since we started talking about this topic. And what did we say? We said these are just three-dimensional regions within subshells where we have a higher probability of finding an electron at a specific time. And what should we know is that each orbital has a specific shape. Each individual orbital has a specific shape, but also orientation in space. And by by having these two characteristics, uh, these orientation and spaces can actually accommodate different amounts of electrons depending on the number of orbitals that you're talking about, or the subshell and orbital. And we've discussed to say there are actually different amount or different numbers of orbitals depending on the subshell that you're talking about. So each individual orbital is having a specific shape, a specific size, and also specific orientation in space, and can accommodate different amounts of electrons depending on what type of subshell you're talking about. So there are four orbitals. We've already talked about them. The first one we're going to look at is what we call the S orbital. So the S orbital, we've said, is spherical in nature. It has a spherical shape. And what else apart from having a spherical shape? And apart from having a spherical shape, what else should we understand about the S orbital is that it has a nucleus at its center. So regardless of the principal NH level that you're looking at, regardless of the shell number that you're looking at, you are going to find that there is always one S orbital in N one or in N S subshell. So each S subshell in each energy level has one S orbital. Like this. And the S orbital can accommodate a maximum of 2 electrons. The maximum number of electrons that can be accommodated in the S orbital is 2 electrons. like this. And they are actually the most basic type of orbitals that you're going to find uh, in an atom. Hence, these guys are forming the initial electron cloud around the nucleus. So if you go in atoms that only have two electrons or less, such as hydrogen, you're going to find that all its electrons are only going to be found where? In the s orbital. Very important one there. We can move on to the next one, which is the p orbital. The p orbital. And these guys said they possess a dumbbell shape. What else do they have apart from a dumbbell shape? This dumbbell shape, for those who know what a dumbbell is, you're going to find something that looks like it's bilobed. I can say that it is having two lobes on the opposite side of the nucleus. So if this is the nucleus of an atom, you're going to have one lobe there and also another lobe down there. So that is just a brief description of what a p orbital is. So within any p subshell, you're going to find three p orbitals. Three. In the s subshell, we only found one s orbital, whilst in p subshell, we're going to find three p orbitals. Let me specify to say three p orbitals. Three p orbitals, which are namely px, py, and p Z. So each of these three orbitals is actually oriented along one of the three perpendicular special axes. So those axes that you learn in physics, the x-axis, the y-axis, and the z-axis is going to contain each one of these. So you're going px is in the x-axis, py is in the y-axis, whilst this other one also pz is in the z-axis. So it is giving them a distinct special orientation as opposed to the s orbitals that we looked at. So due to this, we say p orbitals are directional. Those who have heard of this before, we say p orbitals are directional because of how they are arranged in 3D space. You have one in the x-axis, you have one in the y-axis, whilst you also have another one in the z-axis. And each one of these guys, the px, the py, and the pz, can carry a maximum of two electrons. So we're going to have two electrons here. We're going to have two electrons there, and we're also having two electrons there. And this is going to give us a cumulative number of how many electrons? Of 6 electrons in the p subshell. The p subshell is going to accommodate a maximum of 6 electrons, because each of its three orbitals, namely the px, py, and pz, can actually, accommodate a maximum of 2 electrons. So one important thing that we should also note about p orbitals is that due to this directionalness that we've talked about, due to the directional nature, or the directional nature, we said p orbitals are directional. It makes them actually to be very important in forming covalent bonds that are directional and influencing the overall shape of molecules that you're going to form after bonding of different atoms. The p orbitals are actually very crucial in determining the shape of those molecules because of their nature. We just say these guys are directional, so which means they'll be very critical in giving us the nature of the molecule or the shape of the molecule that we are going to come up at the end of the day. The third one is what we call the d orbital. And what's so special about these d orbitals? We've already said they exhibit more complex shape. They are very complex. But in case you are asked in an exam to say what is the shape of a d orbital, I should just say they have an overcliff shape, or overleaf, or a cloverleaf. Sorry, cloverleaf. A cloverleaf shape. So if they ask you to say what is the shape of the d orbital, you can just say d orbitals have a cloverleaf shape. although one of these 5d orbitals, remember we said there are five in total, or in the d subshell we have 5d orbitals. One of the 5d orbitals has a unique dumbbell shape with a toroidal. Let me write this down. With a toroidal region around the center. So d orbitals are actually very complex. Let me just try and find maybe a shape of a d orbital. Okay, so these are s orbitals. We say they're spherical in nature. Here are the p orbitals. We say they are the px, py, and pz, just like that. Then we have the d orbitals. So we've said they have a cloverleaf shape like this, but one of these guys, which is namely the DZ2, this guy that is here, you can see that it is having a dumbbell shape. This one that is on the center here, whilst at the same time having what I mentioned to be known as a toroidal region within the center, which is this guy that we have here. So this is the shape of the d orbitals and the 5d orbitals that exist. We have 1, 2, 3, 4, and 5. This guy, which is on the center, which is actually looking a bit unique when compared to the other 4 d orbitals. So that is the shape of a d orbital. And what are some of the characteristics of d orbitals that we should take note of? Should we say they are 5? So in the d subshell, there are 5d orbitals. And each of these 5d orbitals can actually also carry a maximum of 2 electrons. And since there are 5, we're going to multiply this by 5 in total. That means the d subshell can actually have a cumulative number of electrons, which is equal to 10 electrons like this in the d subshell. So these are very important when we talk about the chemistry of transitional metals, because you can see to say they are found in mostly big elements, of which one of those is the transitional metals of the periodic table, influencing their unique bonding characteristics, sometimes even the magnetic properties and their ability to catalyze reactions or the catalytic activities of the d orbitals. So that's all I can tell you about d orbitals. Let's quickly look at the last one. This will be quite a long lecture or a long class. Let's look at the last one, which I'm going to call the f orbital. The f orbital. And the shape, this one is even more complicated than the d orbital. So we can just say they are multi-lobed. Multi-lobed orbitals, and there are 7 in total. So in the d subshell, there are 7 d orbitals. There are 7 d orbitals, and each of these 7 d orbitals can also carry a maximum of 2 electrons, which means for us to find the cumulative number of electrons that are accommodated in the d subshell, we're going to say 2 multiplied by 7 to get a total of 14 electrons. 14 electrons in the d subshell, like that. So these are massive orbitals that can carry a maximum of 14 electrons in the f subshell. So these orbitals, mostly their importance is that they apply mostly when you want to understand the the unique chemistry of compounds that we call lanthanides and the actinides, and they're also going to mostly affect their magnetic properties and also their optical properties. So that's all, guys, on the atomic orbitals. We've talked about all the 4 atomic orbitals, their shapes, the suborbitals that they are found in, their amount in each suborbital, and the maximum number of electrons that they are able to carry. Now that we've looked at the quantum numbers, the atomic orbitals themselves, what else would I love us to look at is uh, or the electronic configuration, which are some of the rules that govern the filling of electrons in these spaces that we've just talked about. So this is the next thing that I'm going to talk about, the electronic configuration. And some of the rules that govern the filling of electrons in these spaces that we've described. So, what is or how can we define electronic configuration? This is just a systematic distribution. Let me write the definition: the systematic distribution of electrons amongst various of electrons. Sorry, I can just say of electrons. And since electrons are negatively charged, I'll put a negative there. Like the systematic distribution of electrons among the various atomic orbitals, among various atomic orbitals in an atom. So very important because uh, there are rules that govern the filling of electrons or the distribution of electrons in each and every atom. There are rules that govern this activity or this occurrence. Just doesn't happen in any way. Remember, we've talked about atoms occupying or electrons occupying first the lowest energy levels, and they keep on increasing in that manner. It's because there are rules that govern uh, this distribution. Hence, it is not random, and it is going to adhere to the fundamental principles that we've talked about already, and also some of the rules that I'm going to talk about here. Which one of those rules that govern the distribution of these electrons in the atomic or in the orbitals is what we call the Aufbau principle. The Aufbau principle. The Aufbau principle, and uh, this principle is derived from German language. No, it's German language. I don't know what they call that language, but it just means to build up. So, what does this principle actually dictate? It dictates to say electrons will always occupy the lowest energy atomic orbitals available before filling higher energy orbitals. So, you're going to follow that order from lowest energy orbitals, and they will follow that order, increasing to higher energy orbitals. So that means you can't occupy an orbital that has higher energy if you haven't yet occupied the orbital that has lower energy. You're supposed to follow that order in that manner, which means when you are looking at, let's say you are looking at, maybe you have S, P, and D orbitals. You are first going to start with filling the S orbital or the 1s orbital. Even when you have maybe you have, let's say, in the first shell, we say there's only 1s orbital. You're going to fill this orbital first before you can move on to the second shell, which has the 2s orbital, and you're going to fill this one, the 2s orbital, before you fill the next orbital, which is the 2p orbital. So you're supposed to follow that order. You're going to start with the lowest energy orbital to the highest energy orbital, following that order without skipping any. So that is the Aufbau principle. The next one is what we call the Pauli's exclusion principle. Pauli's exclusion principle. So what does the Pauli's exclusion principle actually talk about? This one states that each atomic orbital can hold a maximum of 2 electrons, and these 2 electrons must possess opposite spins. So for example, what we talked about, so I'll just simplify it as each two electrons occupying the same orbital. The same orbital must have opposite spins. And what does this mean? This means if you have two electrons that are occupying, let's say, the 1s orbital, like this, there are two electrons that are going to be occupying um, uh, this orbital. One electron is going to have a positive half spin, whilst the other orbital should have the negative half spin to balance up this occupation in a single orbital. So the two orbitals that can be occupied in, or that can be accommodated in each orbital, should actually have opposite spins, which means you have one facing up here, whilst another one should be facing down there. And which principle is talking about this? It's the Pauli's exclusion principle. So this is the main thing that the Pauli's exclusion principle actually talks about. The third one is the Hans rule. Or what we call Hans rule. So we can also finish it. So sometimes they'll put it in detail, but just this is enough. But sometimes they'll tell you to say it's the Hans rule of maximum multiplicity. So what does this talk about, or what does this rule actually talk about? It states to say electrons should occupy degenerate orbitals singly with parallel spins before pairing up, minimizing electron to electron repulsion for stability. That's how I can simply explain to you what Hans rule states to say electrons should occupy degenerate orbitals singly and with opposite spins, which is just including the Hans rule. I mean, with the Pauli's exclusion principle. With opposite spins or with parallel spins before pairing up like this. So what does this actually mean? Let me just show you a diagram of the Hans rule. If I have one, obviously. Let me check. No, I think it's on top. Okay, Hans rule, this one. Every orbital in a sublevel should be singly occupied before any orbital is doubly occupied. All the electrons in singly occupied orbitals have the same spin to maximize total spin. So, for example, if we have this p orbital, the 2p orbital here, you should notice that we are filling it singly before we double the filling. If we're talking about the same subshell, for example, the p subshell, which is having 3 orbitals, the electrons should fill these orbitals singly before it doubles the occupation like that. So even when you run out of electrons, you should make sure to say you're following this order. It'll be like that, like that. If you only have three. Let me give, for example, this is a 2p orbital. If you only have three electrons in the 2p orbital, they should do singly occupy those orbitals. Whilst if you have 4, it is going to occupy here. If you have 5, it is going to occupy here. Whilst if it's 6, that means the 2p orbital is full and it is going to finish the occupation in that manner. So that is simplifying the Hans rule, and using these 3 rules that I've talked about, which is the Aufbau principle, the Pauli's exclusion principle, and the Hans rule, we should actually know how each and every electron is going to occupy the atomic orbitals in an atom. And there are examples here of some atoms that are included. Let's say, for example, if you have an atom of carbon, you are going to have three orbitals. You're going to have the 1s orbital, you're going to have the 2s orbital, and you're going to have what? The 2p orbital, like this. And since carbon has in 6 electrons, you're going to, how are they going to occupy these orbitals? You're going to have one there, but since this is on its own, and it's in the first energy level, or in the S shell in the first, or in the S subshell in the first energy level, it is going to be occupied like that. 2s be occupied like that. We are following the alpha principle. We are first filling the orbitals of lowest energy before we go to orbitals of higher energy. Then when we reach the 2p orbital, what are we going to do? We're going to fill these singly first, and we've run out of our electrons. So that means we have 2 electrons in the 1s orbital, we have 2 electrons in the 2s orbital, and we have 2 electrons in the 2p orbital, just like that. So we followed, or we've applied all the three rules that govern the electronic configuration of each and every atom by doing what? By first occupying the lowest energy levels, the lowest energy level orbitals, and from there, making sure that the two orbitals that are, or the 2 electrons that are occupying the same orbital should have the opposite spin. And from there, making sure that the electrons that are filling up degenerate orbitals are first filled singly, as shown here, before we double the filling to maximize the spin and also stability of an atom. So that is all about electronic configurations. There are different examples. You can talk about different atoms like this. All of them are different. Some will even be reaching the d orbitals, but you just have to make sure that you are following these rules. For example, phosphorus it has the 1s orbital, the two in the second shell, or in the second energy level, you have the 2s orbital, or the 2s subshell and the 2p subshell. In the third energy level, you're going to have the 3s subshell and the 3p subshell, and those will be able to occupy or to accommodate all the electrons that are found in the atom of phosphorus. So, ladies and gentlemen, that's all on the electronic configuration of different atoms. You can try and go through some questions to see if you've understood. Just get any random atoms and make sure to say you look at how the electronic configurations of those atoms can actually be. Okay, so apart from that, let's now look at the last thing that I wanted to discuss in today's class. Remember, I told you to say this class will be a bit long, very long actually. I'm used to making 30-minute classes, 1 hour classes, but this one has gone a bit over time. So the last thing I want to talk about is hybridization. Hybridization, a very important concept. It's where you have mixing. Yes, I can call it mixing. You have a mixing of atomic orbitals to form new degenerate hybrid orbitals. What did we say about degenerate orbitals? We said, for example, if you have the p subshell, you have 3p orbitals. So these orbitals that are found in one subshell, these are going to be called the degenerate orbitals. So it's the same thing when it comes to hybridization. You're going to be having uh, the mixing of orbitals to form new degenerate hybrid orbitals, which means you're going to be having maybe the mixing of the p and the s orbitals to form one degenerate orbital that is going to cater for all electrons that needs to be filled in that particular instant. Now, these new hybrid orbitals that are formed, the hybrid orbitals that are formed are going to be having specific shapes and orientations in space. And this is just to allow for the optimum pairing of electrons. And this is going to lead mostly to, or not mostly, but this should lead to stable chemical bonding. Chemical bonds in molecules. So when we have hybridized orbitals, these are going to be specifically formed with a specific shape and orientation, and they are going to allow for the most suitable pairing of electrons in chemical bonds, hence leading to having very much stable chemical bonds in molecules. So, what are some of the functions of these uh, hybridized orbitals, or the purposes of hybridization? One, we are going to use this concept of hybridization to explain why we observe different bond angles, the shape, and the bond angles in molecules. So you can actually explain the shape and bond angles in molecules using the principles of hybridization, because this is going to enable atoms to form stable bonds with correct geometry. Correct geometry. I'm trying to rub something, but it's not going. I don't know why. Yeah, so it is going to lead to stable bonds which are having the correct geometry and also very stable bonding configurations due to lower energy of hybridized orbitals. So these orbitals are going to have low energy in order to spearhead this stability that we're talking about, because the lower the energy of an orbital, the more stable the electrons in that orbital are going to be. So we're having more stable, low hybridized orbitals as opposed to the the pure atomic orbitals that will be in an individual atom. So before we discuss some of the types of hybridization that are there, I'm sure I've already heard about this thing, hybridized orbital, the sp2, blah blah blah, which are just talking about the atoms, or I mean the actual orbitals that will be overlapping to form hybridized orbitals. Let's look at uh, the two main types of covalent bonds that are there. They are what we call sigma bonds. What we call sigma bonds. And what are these bonds? These are the strongest type of covalent bond that you ever find, and it is formed with a direct head-on overlap of atomic orbitals among an internuclear axis. So whenever you find atoms joined by a single bond like this single bond that you are seeing, if it's the only one, that means that bond has been formed by a direct head-on overlap of the atomic orbitals in the internuclear axis. So all the single covalent bonds that you're going to talk about, they actually contain one sigma bond. And when you find that there's a double bond like this second bond that you're going to find is formed by a lateral or sideways overlap of the two um, lobes of the unhybridized p orbitals. So these, or even when you find that you have a triple bond, I don't know if there can be a triple bond between a carbon and a carbon, but it's very possible. You're going to find that one of these bonds that are here have been formed by a direct head-on overlap. So there's a sigma bond, one of them, and the other bond that is going to exist between these two is formed by lateral overlapping of the unhybridized lobes of p orbital. So this one will be a pi bond. Even this one will be a pi bond, whilst one of these will be a sigma bond. Now, the more common types of hybridization that you are going to find, we have what we call the sp hybridization. And what does the sp hybridization involve? This one just involve the mixing of one s, not one s as in the actual one s orbital, but I mean one s orbital, one s orbital, and one p orbital, one p orbital. So when these orbitals mix, they're going to form what we call sp hybridized orbitals. So there's sp hybridization that is taking place here, and mostly in sp hybridization, you're going to find that you're going to have linear molecules. Linear molecular geometry, and one of the good examples that we can give is this guy. It has, or it is having a linear molecule because the hybridization that is there is just sp hybridization. So each carbon in this molecule is going to form a sigma bond with um, a hydrogen and also the other carbon. Therefore, having uh, the two unhybridized p orbitals forming pi bond. Very important. So that is an sp orbital or sp hybridization. You can also find sp2 hybridization, which involves one s orbital and two p orbitals. Two p orbitals to form an sp3 an sp2 hybridized orbital like this, or to form sp3 or sp2 hybrid orbitals. Keep on saying sp3, I don't know why, but it's sp2 hybrid orbitals. And when you have this type of hybridization, you're going to notice that the molecule that you're going to have between the bonding atoms will be what we call the trigonal plan. The trigonal planar like that. So that is resulting due to the sp2 hybridization that is going to take place between these two, or the atoms that are involved in that type of bonding. And this is mainly due to one s orbital and the two p orbitals combining to form sp2 hybridized orbitals, so that they minimize the orbital energy and they form stable bonds. So I want to give examples of molecules that conduct sp2 hybridization because I just want to have an overview of what these hybridizations are. So I have sp3 hybridization, so I have one s orbital and the three p orbitals mixing to form four sp3 hybrid orbitals. So you're going to have this guy. There's one s orbital, then you have this. Okay, is it like this? No, not like this. You have one p orbital that is combining with what? Combining with the three p orbital. So you're going to have 1, 2, 3 like this. One s here is combining with the three p orbitals here to form an sp3 hybrid orbitals or sp3 hybrid orbital, and these you can see to say they will become 4, allowing the actual bonding of the atoms that are involved in the bond to take place like just like that. So if you have sp3 hybridization, the geometry of the molecule that you're going to have is tetrahedral. Tetrahedral. I don't know if I have the diagrams in the other notes. I'll try and check to show you whether they are there. And the other one is also the sp3d hybridization. sp3d hybridization, where you have one s orbital, three p orbitals, and one d orbital. So these guys are going to combine to form sp3 hybrid orbitals. And when you have these orbitals combining to form one orbital, you're going to have a geometry which is known as trigonal, bipyramidal. by pyramidal geometry like that. And the last one, but not the least, I can talk about the sp3d2 hybridization. So we have one s orbital, three p orbitals, and two d orbitals combining to form. How many orbitals are these going to be? Of one s orbital, one, two, three. Okay, like that. So these are the 2d orbitals, 3p orbitals, 1s orbital. So these guys are going to combine to form those degenerate orbitals to allow bonding of atoms. And once you have this type of bonding, the geometry is known as octahedral. Just like that. So that is all about chemical bonding. Thank you very much, guys. We've talked about a lot of things. We've talked about atomic structure itself. I've went through a brief introduction. We've talked about the quantum numbers. We've talked about electronic configurations. We've talked about hybridization itself. And what else am I forgetting? I don't know, but I've forgotten something. Oh, orbitals themselves. So we've talked about all these different things, and I hope at the end of the day you've gotten something. So thank you very much again for watching. Make sure you subscribe and hit the like button, and see you in the next one. So this also marks the end of this topic, which is atomic structure. We already discussed the chemical bonds, and those were the only things that I thought I had forgotten. So thank you very much for being with me, and until next time, stay blessed.